Hey there, you shining star. Welcome to the lab. Okay, step one, analysis of the MATLAB situation. So, we know from the definition of the time constant that it occurs first at 63%, about 63%, the total charge of the capacitor. Additionally, we know it's equal to R times C. So what this demonstrates is with a higher resistor, you have a higher time constant. As you can see, they charge at a slower rate with a higher resistor, meaning that at 63% charge, it will be a higher time for the higher resistor. This essentially demonstrates all the properties needed in this lab for the time constant with these two curves. Moving on, part two, code. Oh, great part. Oh, fantastic part. Okay, so as you can see, we've assigned doubles. We've done very generic things here. Assign output, input using pins 2 and A0 as an input analog pin. And then I've created two for loops. So each for loop lasts as long as the requirement to have it on high and low for the digital pin. And then within that, the loop itself, the parameters of the loop, set the intervals for sensing the analog input, aka the voltage of the capacitor. As you can see, we have one for loop where beforehand it is digital rate to high and afterwards digital rate to low. Moving forward into the processing code, we took the basic steps that are required to hook it up to the right port and everything like that, create the file, and if I run it, as you can see using this circuit, I'm currently using the 10,000 kilo ohm resistor in conjunction with the capacitor needed. You can see the pins and everything. Here's an aerial view with red for input voltage, black for ground, and green for the sensing wire. Moving forward, we have the processing code. In the processing code, if I press run here, you'll see a functioning oscilloscope. It will take a while to kick in, but bear with me. Bear Grylls. There we go, charging, discharging. You can see here that we've labeled everything correctly, and we're at the halfway point for the video, and I still haven't gotten to the example, so that's fantastic. Moving forward, MATLAB code. As you can see, the MATLAB code right here was ran. I used the option 2 for MATLAB via the virtual computer lab, chucked in the file location, pressed run, and up came this beautiful little graph right here. Look at them, all cute. We have on the left volts times 10 to the negative 2 as an adjustment for the ADC to volts, and you can see it charges and then discharges, charges, discharges. Here we have two examples as opposed to, for example, in the lab's example of 3 or 4. Now, if we wanted to sense the time constant, I'm running out of time here, so bear with me, Bear Grylls. Okay. Here, I've written out the steps. Tau is the amount of time at 63% charge. Therefore, given 5 volts is the maximum, we can set up this equation here, where tau, of course, equals RC, the definition, where C in this case is always 10 to the negative 6. And then using the CSV file, we can look into it and find 3.15 as the voltage. Take the time that corresponds to that, and that will be the time constant. Now, this immediately gives us the time constant. Part 2, looking up the resistance. So, to find the resistance, we have T of 6.13, oops, I didn't finish writing this, times 5 volts, over the capacitance, which in this case is 10 to the negative 6. And this will give the resistance without fail each time. Now, when it comes to interacting with the code for this, I'm at 3 minutes and 40 seconds, so I'll be fast, I swear. Don't worry. Okay. When it comes to looking at the code, we know the code is dependent on the time constant for the interval values. However, this doesn't matter. As long as it will reach the first tau value of a time constant of 0.63, we can use the values that are currently in here for all the intervals of sensing. So, as long as we can generate any usable CSV file where we can look up that voltage and see the associated time, we can perform these calculations. Now, do I have time to do this? Here's the question. Can I be like a cheetah here? Whip in a new little thing in this, and then show, probably not. Okay. I guess with my remaining time, I'll talk about the code and what I did a little more, maybe. I kind of explained it, though. Serial print moves, creating a string here. String A, the sensing. String B, the sensing. I used double A equals an actual double value instead of doing a digital read because it's an output pin. I don't mind that. It's my pet. And otherwise, have a wonderful night. This is Lab 5. Go, Terps are fearless.